Welcome to week two of Introduction to Information Theory. I am the. Give me a minute. I am Sachin from the Indian Institute of Science and. Oh my God. Sorry, there was a. Hello, 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 hello. Hello. Um, there were some technical issues with the mic. Uh, Hopefully, it's resolved now. I am Sachin from the AC department in the Indian Institute of Science, and I'll be conducting today's problem solving session for the course noc 25-ee03, Introduction to Information Theory. There will be I'll solve 10 problems from previous year assignments. which will be similar to the questions on your assignments this year. Question 1. Which of the following statements is true? And the options are: in a binary tree of an optimal binary prefix free code, there is no unused leaf. This is a true statement because if there was an unused leaf like this, um, so suppose this corresponded to a code word for some message, then you could easily uh, eliminate the last bit and make this node as a leaf. So that would reduce the code word length for that particular code by one bit, which would mean that your original code was actually not optimal. So it is a true statement. The second option is there exists an optimal binary prefix free code such that the two least likely code words only differ in the last digit. This is also true because we know that there cannot be an unused leaf. So at the maximum depth, there must be two leaves like this, which are both code words. Consider any two code words like this. Then uh, you could replace, you could swap um, these code words with the code words for the least likely messages. That is, suppose this is a code word for message UI and this is the code word for message UJ, and suppose UK minus 1 and UK are the least likely code words. Wherever they are, wherever the code words for UK and UK minus 1 are in the binary tree, you could always swap. Uh, let's say you have a code word for, in some level, code word for UK, and some other level you have a code word for UK minus 1. You could always swap the code words around. So let's say you put UI here and UK here, and you swap these code words UK minus 1 and UJ. Now, uh, effectively, the sum, code word length, average code word length will decrease by doing such a swap because uh, the lower probability messages are being assigned higher probability, higher length code words. So in the overall sum, the average code word length, which is summation of WIP PU of UI, uh, earlier the least likely code words UK and UK minus one had smaller uh, lengths and um, more probable code words UI and UJ had larger lengths. Now, since we swapped those around, the overall sum WIPU of UI will go down. For example, if the maximum depth is 3 and these are code words of length 3 and UI and UJ, UK and UK minus 1 were initially assigned code words of length 2. Suppose all of these had probabilities zero point 0.2 and these had probabilities zero point 0.1. Then the contribution in the from UI, UJ, UK, and UK minus 1 in the original code, in this code would be towards the average code word length. This would be 3 into zero point 0.2 twice plus 2 into zero point 0.1 twice, which is 2 times zero point 0.6 plus zero point 0.2, which is 1.6. Now suppose you swap the code words around such that UK and UK minus 1 with probability zero point 0.1 have code words of length 3 and UI UJ which have a probability zero point 0.2 have code words of length 2, then the average code word length contribution from these code words to the average code word length would be again 2 times 3 into zero point 0.1 plus 2 into zero point 0.2, which is 2 times zero point 0.3 plus zero point 0.4, which is 1.4. So the average contribution from these code word, from these from the messages assigned to these from the code words assigned to these messages is lower in the second case. So the first case was actually not optimal. So in an optimal binary prefix free code, you can always swap the least like code words assigned to the least likely messages with the longest length code words in the tree. So option B is also a true statement. Next option C says there are at most D minus 2 unused leaves in the tree of an optimal prefix VDRE code, and all are at maximum length. Now here again, suppose you had a leaf that was not at maximum length. So this is at length 3. So this is the code word 00 is for message U1 and code word 01 is for message U2. If you assign code words like this and leave this leaf empty, which is not at maximum there, then you could easily swap the code words around so that you leave that particular this particular leaf empty and assign this code word to U1, assign this code word to U2. Now U2 has been assigned a smaller length code word, so uh, the average code word length will always decrease regardless of the probability value for U1 and U2. So this clearly cannot be optimal. So if there is an unused leaf that is not at maximum length, you can take a maximum length code word. You can take a message which has been assigned a maximum length code word and assign the unused leaf as a code word for that. So here you could have switched U1 or U2 to this place, U1 or U2. That would decrease the overall code word length. That's why the unused leaves must be at maximum length for an optimal code. Once that is out of the way, there must, if there are d minus 1 unused leaves, d minus 1 or d unused leaves at maximum length, then you could swap the code words around at maximum length such that all those unused leaves are uh, originating from the same node. Then there will be at most one code word here, and the rest are all unused leaves. Or if there are d unused leaves, you will get a node from which there are no code words. In that case, you can eliminate uh, the entire. In the second case, you can eliminate all these unused leaves and replace them with the node as a unused leaf. Or if there was only a single, if there are d minus 1 unused leaves at the maximum length, then you can swap them, swap the code words around such that uh, there is a node where only one code word exists and the d minus 1 leaves are all unused. In which case, you can easily uh, make this node as the code word, which reduces the. So suppose U1 was assigned this code word, you could uh, remove the last bit and assign the node itself as the code word for U1. So you can have at most d minus 2 unused leaves in the tree for an optimal prefix-free dairy code. So that's also a true statement, and that would mean that option D, all of the above, is the correct answer. Next, we'll move on to question number 2. The average code word length, expected value of W of any DARE prefix-free code for a carry random variable U with entropy h of x with the base D satisfies uh, which of the following options? So the lower bound and upper bound for the average code word length EFW was already derived in class, and the formula for and the bounds are the average code word length is greater than or equal to h of x by log d and less than h of x divided by log d plus 1, where h of x and log d must be to the same base. So if we take the base to be equal to d, log d to base d is 1, then we would have expected value of w, which is the average code word length, would be greater than or equal to hd of x. So the lower bound is with, there's a possibility to match the lower bound, so you have an equality there. But the upper bound cannot be matched. It's a strict inequality, which is hd of x plus 1. So the right answer is option B. So the it's an easy question. You just have to take base of the logarithm to be d, and then you have to remember which is the bound is exact and which is a strict bound, or which of the bound can be achieved and which one is a strict inequality. So in this case, the lower bound can be achieved. So in case the probability distribution of the code words is of a certain pattern, so there do exist probability distributions for which you can get the lowest expected code word length, but you can never match the upper bound. Question 3 is design an memory code for an alphabet of size 6 with code word length 111222. What is the smallest value of D for which you could design a uniquely decodable code? Here, uniquely decodable code would mean it's a prefix-free code. Options are 2, 3, 4, 5. So there's no good method really to solve this other than trial and error. The main point you have to keep in mind is Raph's inequality, which says that a prefix-free code, which is a uniquely decodable code, exists if summation of d power minus wi, where I ranges from 1 to k, where k is the number of messages, is less than or equal to 1. So here you can see that there are 6 messages, and the code word lengths are 111222. So 1 over d plus 1 over d plus 1 over d plus 1 over d square plus 1 over d square plus 1 over d square must be less than or equal to 1, which is 3d plus 1 less than or equal to d square, or d square minus 3d plus 1 greater than or equal to 0. But here d has to be an integer, since d is the number of values that your output alphabet has. So you could try for different values of d. So d is equal to 1, then d square minus 3d plus 1 is 1 minus 3 plus 1, which is minus 1. So that's not enough. D is equal to 2, that's 4 minus 6 plus 1, which is minus 1, which is less than 0. So d is equal to 2 is also not enough. D is equal to 3, you get 9 minus 9 plus 1, which is 1. Let me see, maybe I made a mistake somewhere. This was 1 over d plus 1 over d plus 1 over d plus 1 over d square plus 1 over d square plus 1 over d square. Okay. Um, just 3 by d plus 3 by d square less than or equal to 1, which is 3d plus 3 less than or equal to d square. So this is actually, sorry for that, this is actually d square minus 3d minus 3 should be greater or equal to 0. So in fact this is -3, or d is equal to 1, this is 1 minus 3, which is -5 less than 0. D is equal to 2, it's 4 minus 6 minus 3, which is -5, which is also less than 0. D is equal to 3, it's 9 minus 9 minus 3, which is -3, which is also negative. So D is equal to 3 is not enough. D is equal to 4, we have 16 minus 12 minus 3, which is 1, which is positive. So D is equal to 1, D is equal to 4 is enough to give us uh, a code, a byte prefix free code. So the answer is option C, D is equal to 4. Or if you don't want to do trial and error, if you're able to split this into factors, so here there are no easy factors, but in case you had something like d square minus d square minus b minus 2 or something like that, then you could split that into d square minus 2d plus d minus 2, d plus 1 and d minus 2 greater than or equal to 0, and then you can analyze the graph of that and find for which values uh, that inequality holds. Otherwise, if you have a quadratic equation that, or a it only turned out to be quadratic because the code word lengths were only 1 and 2. It's if there are code words of length 3 or 4, then it will turn into a much higher degree polynomial equation, in which case you can't really reduce the equation easily. So you will have to go by trial and error. But as far as the course is concerned, you won't have complicated questions. So within 4 or 5 values, you should be able to get the right answer. As you can see, the option is only up to d is equal to 5. So you would have to try from d is equal to 1 to d is equal to 5, and you would have your answer. Question 4. Consider the following codes. You have codes, and these are symbols. So symbol A, B, C, D are the 4 symbols. And you have 4 different coding schemes. The first scheme assigns the code words 0, 0, 1, 1, 1, 1, 1, 1 respectively to A, B, C, and D. So these are the symbols. This is one particular code which assigns these code words to these symbols. So the code 1, Roman numeral 1, assigns um, a single bit 0 to the symbol A, 0 1 to symbol B, 1 1 to symbol C, and 1 1 1 to symbol D. The second code assigns 0 to A, 0 1 to B, 1 1 0 to C, and 1 1 1 to D. Third code assigns 0 to A, 1 0 to B, 1 1 0 to C, and 1 1 1 to D. Fourth code assigns 1 to A, 1 0 to B, 1 1 0 to C, and 1 1 1 to D. The question is, which of the following statements is true? Options are: only 3 is uniquely decodable, only 1 and 2 are uniquely decodable, only 3 and 4 are uniquely decodable. Final option is all the above codes are uniquely decodable. So a code is uniquely decodable if it's a prefix-free code. That is, any none of the code words is a prefix for any other code word. For example, here 0 is a code word for A, but 0 again occurs right at the beginning of the code word for B. So this could cause a problem when you're sending a large number of code words. You may not be able to distinguish uh, between different sequences of code words. For example, suppose consider the first code. Suppose you receive a sequence such as this: 0011. Now, is this 00 and 111? That is, did the sender transmit AAD, or did he actually transmit 0, 01, and 11? So, did he transmit ABC? So, we can't tell directly from looking at the bit stream. So, you would have to have some kind of demarcation in the bit stream if you wanted to know. So, that might cause just a lot of synchronization problems. So unless you know exactly where to stop, if someone actually told you that you have to stop here and here, then you could decode it properly. But if you are just receiving a stream of bits and you have to start decoding, then you can't really tell whether the sender transmitted AAD or ABC. So this is true for second code also, where A has 0, B is assigned 0, 1, C has been assigned 1, 1, 0, and D has been assigned 1, 1, 1. So if you receive 01110, you can't tell if that is 01110, which would be BC, or 0111 and 0, which is ADA. So you can't tell just by looking at the bit stream which of these sequences are actually sent. The same thing with code number 4. In code number 4, we have A as 1, B is 10, C is 110, D is 111. So if you send 110110, you can't tell whether this is A, B, C, or just C twice. So these are all not prefix-free codes. So they are not uniquely decodable. Only difference, only other option 3 is actually a prefix-free code because 0 is not a prefix of any of the other code words. 10 is not a prefix of C or D, and 110 is not a prefix of D. So none of the code words is a prefix of any of the other code words. Therefore, the 3 is a prefix-free code. Therefore, 3 is uniquely decodable. Question 5. A discrete memoryless source emits a symbol U that takes 6 different values U1, U2, U3, U4, U5, U6 with probabilities 1 over 4, 1 over 4, 1 over 8, 1 over 8, 1 over 8, and 1 over 8, respectively. A binary Shannon-Fano code consists of code words of what length? The options are all the code words are of the same length. This just by inspection you can see that that's probably not right because all of them don't have the same probability. An optimum code would assign different code words, different length code words to messages with different probabilities. So option B is also by inspection not correct. So we can straight away eliminate option A and option B. That leaves us with option C and D. And you can see that all the code words with probability 1/8 are assigned a particular length, and all the all the messages with probability 1/4 are assigned a different length. So both option C and D are reasonable. But the coding done here is Shannon-Faro coding, where the length is the ceiling of minus log of p of ui. Since it's binary, the base is 2. So w1 is ceiling of log of 1 over 4. The ceiling of log 4, which is 2 bits. So from that we can see the right answer is option C. We can also check what the code word length is for the messages with probability 1/8, and there will be ceiling of log 8, which is 3 bits. So the messages with probability 1 over 4 are assigned 2 bits and 2-bit code words, and messages with probability 1 over 8 are assigned 4-bit code words. Therefore, the answer is option C. A discrete memoryless source emits a symbol U that takes 6 different values U1, U2, U3, U4, U5, U6 with probabilities 1 by 4, 1 by 4, 1 by 8, 1 by 8, 1 by 8, and 1 by 8, respectively. A Fourier Shannon-Fano code consists of code words of what length? Which length? What length? Not sure what the right word is. Options are again 111222. This by inspection you can say that's wrong because again Shannon-Fano coding, the Code word length depends on the probabilities, and the messages with same probability are assigned code words of same length. So the first two messages which have probability 1 over 4 must be assigned code words of one particular length, and the last four messages which have probability 1 over 8 must be assigned code words of a different length, and the code words assigned to the lesser probability messages must be larger. So 111222 is out of the is not right just by inspection. Could be 112222 option B, or 223333, or 112233. Again, this is also ruled out for the same reason as option A is ruled out. Similar to the previous question, the code word length of the ith message wi is nothing but the series of log of 1 over pu of ui to base d, where your output symbols are d. Now d is 4 because we want 4 Shannon-Farrow code. So we get w1 is equal to w2, which is seeding of log of 1 over 4 to base 4, the seeding of log 4 to base 4, which is 1 bit. W3, 4, 5, and 6 are of length seeding of log of 1 over 1 over 8 to base 4, seeding of log 8 to base 4. One small change here is that it's not actually a bit because it's a 4-ary alphabet. So it's from F4, some symbol from maybe finite field 4, some symbol from alphabet of 4 elements. So it's not a bit. Length is just one symbol from the output alphabet. Now log 8 to base 4. is nothing but log 8 base 2 by log 4 base 2, which is string of 3 over 2, ceiling of 1.5, so which is 2. So the ceiling is important here, otherwise you would think that length of this, you would get 1.5 instead of 2. But here W's are actually length and lengths are integers. Uh, Lengths in the sense these are the number of bits or the number of symbols from the output alphabet that you need to use. So the number of symbols is always a whole number. So you can't really use 1.5 symbols. That's why you need two symbols. So the correct answer is option B. That's one thing you need to take out of when doing Shannon Phantom coding. The lengths WI are integers because they're actually not lengths in the sense of Euclidean distance or lengths in the normal physical sense. They are lengths of code words, which is actually the number of symbols needed from the output alphabet to express one code word. I'll take a small break and come back after 10 minutes and solve the remaining questions. All right, I am back. Let's start again. Hello. Okay, I'm switching to the microphones in my headset. Sometimes it switches back to the laptop microphone, which is not very clear. Anyway, question 7 is, what is the average code word length for the Shannon-Fano code designed in question 6? Is it 1, 1.5, 2, or 2.5 in terms of symbols from the output alphabet? The solution is the average code word length E of W, that is expected value of W, is the summation of Wi times probability that symbol UI, message UI is transmitted for all messages, and there are 6 messages. So now the symbol UI, U1, U2, U3, U4, U5, U6. The probability of UI occurring is a quarter for the first 2 messages and an eighth for the next 4 messages. The corresponding code word length are 1 for the first 2 messages, 1 symbol from the output alphabet, and 2 for the next 4 messages. From that you can calculate expected value of W to be 1/4 times 1 plus 1/4 times 1 plus 2 times 1/8, 4 times. So it's 2 times a quarter plus 4 times a quarter. It's 6 over 4, which is 1.5. That's option B. Question number 8. A discrete memoryless source emits a symbol capital U that takes 6 different values: U1, U2, U3, U4, U5, U6 with probabilities similar to the previous questions. 1/4, 1/8, 1/8, 1/8 and 1/8 respectively. If binary Huffman code is used for encoding the symbol, what are the possible code word lengths? Options are 223333, 222233, 113333, all of the above. To do Huffman coding in the binary case, you arrange the probabilities The question is, do binary Huffman coding for a memoryless source with 6 different messages with probabilities 1/4 for the first 2 messages and 1/8 for the next 4 messages. The probability distribution is 1/4, 1/4, and 1/8 4 times. And the question is, what are the code word lines if you do Huffman coding in this case? So to do Huffman coding, you arrange the probabilities in ascending or descending order, whichever order you like. So let's uh, U1 has probability 1/4, U2 also, and 1/8 for the next 4 messages. And you draw a vertex for each message. Then you find two least likely code words, that is, two code words with the smallest probability. So if you arrange in descending order, then it's the last two code words and join both of them, and the probability of that node will be the sum of the probabilities of the 2 messages, which is 1/8 plus 1/8. That's 1/4. Now you ignore this part and consider this as your vertex. So you have one, two, three, four, five vertices now, and you repeat the procedure again. You find the least likely, two of the least likely vertices. So two vertices with probability 1 over 4. Again, you have multiple options to do it in each step if there are multiple vertices with the same probability. So you could pick this, this, and this, any two of those. The first stage also, probability, lowest probability was 1 over 8, and that was for four different messages. So you could pick any two of these and join them. The choice is up to you. Depending on your choice, you will get a different code. Okay, now two least likely code words are U3 and U4, which have probability 1 over 8. So join them. That node will have probability 1 over 4. Now ignore these. Consider these vertices. The lowest two probabilities among them are all of them are 1 over 4, so you can pick any two of them. I'll pick these two, and their probability is half. Now ignore these, and we're left with 1, 2, and 3 vertices, of which the lowest two probabilities are 1 over 4 and 1 over 4 for U1 and U2. So join those two, and the node, attach a node to them. Ignore those vertices and consider the node as your vertex. So you have only two vertices left. At that stage, you just join the two vertices to the root. Root has probability. Root node has probability 1. And that gives you your Huffman code. At least it gives you the tree for your Huffman code, from which you have to read off the code words. So this branch is branch 0, this is branch 1. Let me erase the probabilities. And then branch 0 again branches out into 0 and 1. This branches out into 0 and 1. Now we can write down the code words. So for U1, the code word is from the root node, move along the branches to your message and read off the bit on that branch. So the code word for message U1 is 00. For message U2, start here and go this way. So the code word is 01. Then for U3, 100. U4, 101. Code word for U5 is 110. Code word for U6 is 111. And that gives you the code. The question is actually the code word length. So you have first two messages have code word length 2, and the remaining four messages have code word length 3. So the code word lengths are 22 and 3333, which is option A. And that's how you do Huffman coding in the binary case. Question number 9 is Huffman coding, but instead of binary Huffman code, you're going to do 4-array Huffman code. So instead of binary, this is 4-array. And again, you have to find the lengths of the code words. The options in this case are 111222, 112222, 112223, 112233. So to do D-array Huffman coding, first you have to find the number of unused leaves, which you can do by calculating the remainder when you divide k minus d into d minus 2 by d minus 1. So k is the number of message symbols 6, d is the alphabet size of the output alphabet, which is 4 because it's 4-array coding. So k minus d into d minus 2 is 2 into 2 is 4, d minus 1 is 3, which is d minus 1 plus 1. So now the remainder here is r, so r is equal to 1. Again, to do Huffman coding, we arrange the probabilities in descending order or ascending order, any order you like actually, but arranging in descending order is makes it easier. Then in the first stage, the difference between binary Huffman coding and 4-array Huffman coding is that the number of nodes that you are connecting in the first stage is different. In each stage is different. The first in binary Huffman coding, in each stage you are connecting two least likely code words or two least likely nodes or vertices. Here in the first stage you have to connect d minus r vertices, which are least likely. So d is 4, therefore d minus r is 4 minus 1 3. So first you have to connect three least likely vertices, but since it's a 4-array tree, that means there is one vertex that is not used, so there's an unused leaf there. Now the probability of the node connecting these vertices is 3 by 8. Is 0.375. is 0.25, 0.125 is 0.375. Now in the next stages you have to connect D nodes together, where D is 4. Uh, so once you ignore this, after the first iteration, you consider the node connecting the 4 vertices in the previous stage and the remaining vertices. There are only 4 vertices, so you have to join all of them. So we end up joining all these. And that is connected to your root node. So suppose your output alphabet is 0, 1, 2, 3, which is 4 array. This would be 0, 1, 2, 3, 0, 1, 2, 3, and the code words would be for U1 is 0, U2 is 1, U3 is 2, U4 is 3, 0, U5 is 3, 1, U6 is 3, 2. So the first 3 messages have code word length 1 and the last 3 messages have code word length 2. Therefore, the answer is 111222, which is option A. Final question. Average code word length for the Huffman code designed in the question 9 is, options are 0.75, 1, 1.375, and 2. Solution is, there were 3 code words of length 1, out of which 2. Okay, let's just write it down. U1, U2, U3, U4, U5, U6. These are 6 messages. Their probabilities PU of UI are 1 over 4, 1 over 4, 1 over 8, 1 over 8, 1 over 8, and 1 over 8. And the code word lengths WI are 1, 1, 1, 2, 2, 2, which gives you expected value of code word length summation of P of UI times WI equals from 1 to 6 is 1 by 4 plus 1 by 4 plus 1 by 8 plus 2 times 1 by 8 plus 2 times 1 by 8 plus 2 times 1 by 8, which is half plus 1 plus 6, 7 by 8, which is 11 over 8, 1.375, which is option C. So the thing you have to notice here is from question number 2, you have the bounds EFW. And what is EFW? So in questions 5 to 10, you had probability distribution P was distributed according to this distribution 1 over 4, 1 over 4, 1 over 8, 1 over 8, 1 over 8, and 1 over 8. So the entropy HFU was 1 over 4 log 4 twice and 4 times 1 over 8 log 8. Take it in bits. This is half times 2 plus half times 3 is 2.5 bits. This is it's 2 of you. Now if D is equal to 2, E of W greater than or equal to H of U by H2 of U less than or equal to H2 of U plus 1. So expected value of W is between 2.5 and 3.5 bits. So in Q5 we did Shannon-Fano coding, which is binary. E of W was two of the length of first two code words was 2, 2 into 1 over 4, 2 times, and length of the last word code words was 3, 3 into 1 over 8, 4 times, which is 8 plus 12 over 8, 20 over 8, 5 by 2, 2.5. So by doing Shannon-Fano coding, we were able to achieve the lower bound. And in Q8, we did binary half-band code. And EFW is again, we had uh, 2-bit code words for messages with probability 1 over 4 and 3-bit code words for messages with 1 over 8. So the expected value was 2.5. So we meet the lower bound. Both Shannon-Fano coding and binary Huffman codes were optimal in that case. This happens because the probability of each of the messages is an inverse power of the alphabet size. So alphabet size of output is 2, and the probability of each message is a power of 2, negative power of 2. So in that case, your Shannon-Fano coding and Huffman coding both are optimal and reach the lower bound. But it changes if D is equal to 4. In case D is equal to 4, E of W is between H2 of U by log 4 and H2 of U by log 4 plus 1. So if E of W is between H2 of U is 2.5, log 4 is 2. So this is between 1.25 and 2.25. So we saw in question 6 for a Shannon-Fano coding that E of W was one symbol code for messages with priority 1/4 and two symbol codes for messages with priority 1/8. So it was a half plus 1, which is 1.5, which is greater than the lower bound 1.25. And from question 9, we saw for the Huffman code, and that gave you the average code word length of one symbol for the first two code words of priority 1 over 4, one symbol for one of the messages with priority 1/8, and two symbols for the rest of the messages with priority 1/8, which was 1.375, is greater than again the lower bound. So Huffman coding is the optimal and it can't reach the lower bound. So the lower bound is not met. But this is the optimal. So the lower bound was not tight in this case. And also 1.375 less than 1.5. So optimal, which is Huffman, and Shannon-Fano was actually suboptimal. And this is because the probability of each message is not a power of negative power of the number of negative power of the alphabet size of the output alphabet. Output alphabet is 4 array. 1 over 8 is not 1 over 4 power any negative integer. 1 over 4 is 4 power minus 1, but 1 over 8 is not 4 power minus 2 or 4 power minus 3, any of those. That's why in this case, the lower bound is not reached. And also, Shannon-Fano coding gives you different uh, code word length than Huffman coding. I think that's all for today, and I'll see you in the next session.